There is a warship steaming somewhere in the Western Pacific right now that costs roughly $2 billion to build, carries one of the most sophisticated combat systems ever put to sea, and is deliberately, intentionally heavier than it needs to be. The engineers who designed it knew exactly what that weight would cost. They ran the numbers. They accepted slower top speed, reduced range margin, a harder stability calculation. They built the ship heavier on purpose, and then kept building the same ship again and again for 4 decades. The Arleigh Burke class destroyer. 69 commissioned hulls as of mid-2026, with more on order. The most produced large surface combatant in American naval history. And at its heart sits a decision that looks, on the surface, like a straightforward engineering mistake. Except it isn't. It's the answer to a problem that gets more expensive every year. Here's the paradox. Aluminum is lighter than steel. Lighter ships go faster. Faster ships are harder to hit. The US Navy knew all of this in the 1960s. They built aluminum superstructures into their most advanced frigates and cruisers. Then something happened that changed the calculation permanently, and the Navy spent the next generation welding steel plate over the decision they'd already made. What did they learn? And what does it mean for the fleet being built right now to face a rival launching warships faster than any nation since the Second World War? That's what we're going to trace, layer by layer. To understand the steel choice, you have to go back to what aluminum was supposed to solve. Through the 1950s and into the 1960s, the US Navy faced a straightforward physics problem. Warships were getting heavier. Radar systems, missile launchers, fire control computers, magazines. All of it was piling onto hulls designed for an earlier era. Top weight, mass sitting above the waterline, was pushing stability margins into uncomfortable territory. A ship too heavy at the top rolls sluggishly, recovers slowly, and in bad weather becomes a liability. Aluminum offered an elegant exit. At roughly 1/3 the density of steel, it could do the structural work of a superstructure at a fraction of the weight. The Forrest Sherman-class destroyers used it. The Leahy-class guided missile cruisers used it. So did the Belknap class. The Navy wasn't being reckless. It was solving a real engineering constraint with a material that, by every peacetime metric, was the right answer. The Arleigh Burke class has its origins in a 1970s program requirement, shaped by lessons the fleet was still absorbing from the previous decade's combat experience. But the full reckoning with aluminum came not in a design office, but in a fire. June 2, 1975. USS Belknap, a guided missile cruiser, collides with the aircraft carrier USS John F. Kennedy in the Tyrrhenian Sea during night operations. The collision tears open the Belknap's aluminum superstructure, and fuel from the carrier ignites. The fire that follows does something steel would have resisted for far longer. It melts the ship's upper structure. Aluminum melts at roughly 660 degrees Celsius. The fires aboard Belknap burn well past that threshold. The superstructure collapses. 7 sailors die. The damage is so extensive that reconstruction nearly costs more than building new. The Belknap incident is not the first data point. USS Forrestal's 1967 fire. USS Enterprise's 1969 fire. The Royal Navy's Falklands campaign in 1982, where HMS Sheffield and HMS Coventry, both with aluminum structural elements, suffer catastrophic damage from Exocet missiles that a steel hull might have contained better. Each event adds to the same column in the engineering ledger. Here's the part that doesn't make sense on the surface. Aluminum doesn't burn the way wood or fuel burns. It doesn't ignite easily. The problem is what happens when a fire that starts somewhere else, from fuel, from munitions, from a missile hit, reaches an aluminum structure. Steel holds its structural integrity past 1,400 degrees Celsius. Aluminum loses it around 200 degrees, well before it reaches melting point. The superstructure doesn't have to melt to fail. It just has to soften. In a modern warship, structural failure above the waterline isn't an inconvenience. It's a mission kill. Radar arrays, combat information centers, fire control systems, communications, nodes. All of it lives up there. The aluminum saved weight on the way to the fight. The fire took the fight away. When the Arleigh Burke design was finalized in the 1980s, this was the institutional memory the engineers were working against. The DDG-X program, led by a design team under pressure to create a survivable ship at a manageable cost, made the call, all steel construction. The superstructure, the deck houses, Everything above the main deck, steel. The weight penalty is real and documented. The Burke-class flight ice ships displace roughly 8,300 tons full load. An equivalent aluminum superstructure design would have come in somewhere in the range of several hundred tons lighter. Estimates vary, but naval architects consistently cite 300 to 500 tons for a hull this size. That's not an abstraction. That's top speed, range, and the stability margin that determines how many additional systems you can add before the ship runs out of room to grow. The Navy accepted every one of those costs. And for the first decade of Burke-class service, the decision sat quietly in the engineering record, rarely debated in public, largely vindicated by the absence of the disaster it was designed to prevent. Then the threat changed. The Arleigh Burke was designed when the primary threat to a surface combatant was a Soviet naval aviation strike, large anti-ship missiles launched from backfire bombers or submarines at range, tracked by Aegis and engaged by SM-2 interceptors well before they reached the ship. The physics of that threat favored a robust, survivable hull. You wanted to still be fighting after the first exchange. Steel was the right answer. What the 1980s threat model didn't fully anticipate was the proliferation of cheap, accurate, and numerous threats that define the 2020s operating environment. The scenario that planners in the Pentagon now run most frequently isn't a single Soviet-style saturation strike. It's a layered attack combining ballistic anti-ship missiles. Weapons like the Chinese DF-21D range exceeding 1,500 kilometers. With subsonic cruise missiles, supersonic sea skimmers, and swarms of low-cost unmanned systems designed not necessarily to sink a ship, but to start fires. Start fires on a steel ship, and you have a damage control problem. Start fires on a ship with aluminum structural elements, and you potentially have a structural collapse problem. The Burke's all-steel construction was an answer to a threat that, by a different route, became the defining threat of the era it now operates in. Here's what most people assume about modern naval missile defense: that the Aegis system's job is to prevent any hit at all. That's the aspiration. But the engineering baseline, the survivability requirement baked into the hull itself, is built on a different question. What happens if something gets through? I spent considerable time working through declassified naval architecture analyses and congressional testimony on DDG-X survivability, and one detail kept appearing. The survivability specification written into the Burke-class requirement explicitly anticipated hits and fires. The ship was not designed to be unhittable. It was designed to keep fighting after being hit. Steel is a large part of why that specification is achievable. A fire in a compartment aboard an Arleigh Burke can be fought with some confidence that the overhead structure isn't going to lose integrity and collapse onto the damage control team. That's not a small thing. That's the difference between a crew that can save its ship and a crew that cannot. The obstacle the Navy faced in the late 1980s wasn't purely technical, it was budgetary. Steel construction is more expensive to fabricate and more labor-intensive to weld than aluminum. The DDG-X program was already under cost pressure. The first ship, USS Arleigh Burke, commissioned in 1991, came in at around $1.1 billion in then-year dollars, a figure that attracted congressional scrutiny. Adding hundreds of tons of steel to a hull design that could have been lighter was a choice the program office had to defend, line item by line item, against an acquisition bureaucracy simultaneously asking why the ship wasn't cheaper. The program office's answer was essentially actuarial. A ship lost to a structural fire is worth zero. A ship that costs 3% more to build but survives its first missile hit and stays in the fight is worth the full value of its combat system, its crew's training, its $2 billion price tag. The steel wasn't overhead. It was insurance. And unlike most insurance, it was also tactically relevant. A surviving, fighting ship changes the engagement in a way a sunk or disabled one cannot. What strikes me about this choice is how clearly it reflects a philosophy that has become harder to sustain as costs have risen. In the 1980s, the Navy could absorb a top-weight penalty and a cost increment because it was building enough hulls to spread the decision across a fleet large enough to matter. 50-plus Burkes amortize that kind of engineering trade-off. The logic holds differently when you're building 2 or 3 hulls a year and each one costs twice what the first one did. The top-weight problem doesn't go away. It compounds. An Arleigh Burke Flight I, commissioned in the early 1990s, carries a specific radar suite, a specific missile magazine, a specific sensor fit. By the time the Navy reaches Flight High AA in the early 2000s, The ship is carrying additional systems: the SPY-1DV radar upgrade, additional electronics, modified deckhouse geometry. Each addition sits at the top of the ship. Each addition consumes stability margin. Each addition buys capability in exchange for a fraction of the growth reserve the hull started with. The Flight 3 Burke, the current production variant, represents the outer edge of what the DDG-51 hull can absorb. The AN/SPY-6V1 air and missile defense radar, the AMDR, is substantially larger and heavier than the SPY-1D it replaces. Installing it required structural reinforcement of the deckhouse, additional cooling infrastructure, and a power generation upgrade. The ship is heavier than any previous Burke variant. It's also more capable than any previous Burke variant. But the margin for the next edition, whatever that turns out to be, is narrower than it was for Flight Type A. This is the steel paradox closing on itself. The Navy chose steel for survivability. Steel added weight. Weight consumed growth margin. Growth margin is what you spend on new capability. And the ship that survives its fires is running out of room to carry the systems that are supposed to prevent the fires from starting. The Phalanx CIWS, the 20 close-in weapon system that provides the last line of kinetic defense against incoming missiles, weighs roughly 6,200 pounds per mount. The evolved CRAM, which fires rolling airframe missiles and provides a step up in engagement range from the Phalanx, weighs more. Every additional defensive layer you add to the ship is consuming the budget the hull started with, a budget that steel construction made tighter from day one. Here's the part that still doesn't sit right even after you understand the logic. The entire survivability architecture of the Burke class was built around surviving a hit from a threat that, in 2026, costs less than $50,000 to build. A low-cost anti-ship drone. The kind deployed in large numbers across multiple recent conflicts. The kind that Chinese shipbuilders and Iranian engineers have iterated on at industrial scale, can carry an incendiary payload sufficient to start the fire that the steel superstructure is designed to contain. The steel contains the fire. The steel does not prevent the fire. And the ship's primary defense against that $50,000 drone is a chain of systems. Aegis detection, SM-6 interceptors at over $2 million per round, Phalanx as a last resort, that collectively cost orders of magnitude more than the threat they're engaging. The math runs in the wrong direction, and it's been running that way long enough to have its own name in defense economics, the cost-exchange ratio problem. A Burke class at full combat load carries approximately 96 MiG-41 vertical launch system cells. Those cells hold a mix of SM-2 and SM-6 interceptors, Tomahawk cruise missiles, and ASROC anti-submarine weapons. The exact loadout is classified, but the constraint is arithmetic: 96 cells, finite. An adversary who can force the ship to expend interceptors faster than they can be replenished isn't trying to sink the ship, they're trying to empty it. The economic argument for steel construction gets more complicated when you place it next to the shipbuilding numbers that define the current competition in the Pacific. Chinese naval shipyards, facilities in Dalian, Jiangnan, Hudong Zhonghua, are producing surface combatants at a rate that has no modern Western parallel. The People's Liberation Army Navy commissioned more tonnage in a single recent year than the U.S. Navy commissioned in the preceding three combined. The Type 055 destroyer, China's current large surface combatant class, displaces over 12,000 tons and carries 112 VLS cells, more than the Burke. China currently operates over a dozen Type 055 hulls, with more under construction. The U.S. industrial base that builds Arleigh Burkes operates under different constraints. Bath Iron Works in Maine and Huntington Ingalls Industries in Mississippi share the DDG-51 contract. At peak production, the program has delivered 2 to 3 hulls per year. Workforce shortages, supply chain disruptions, and the complexity of Flight 3 systems have at times pushed that number lower. The average cost of a Flight 3 Burke, as of the most recent congressional budget justification available, runs approximately $2.2 billion per hull. Steel fabrication is a meaningful fraction of that cost and that schedule. The welding required to build an all-steel warship superstructure is skilled, slow, and difficult to accelerate without compromising the quality standards that survivability specifications demand. This isn't an abstraction. Congressional oversight reports on DDG-51 have repeatedly flagged fabrication quality as a schedule risk. The material choice that makes the ship harder to destroy also makes it harder and slower to build. Here's a take that will probably draw argument. The steel decision, evaluated as a naval engineering choice, was correct in 1985 and remains defensible in 2026. The decision that's harder to defend is the one that kept the same hull in production for 4 decades without a parallel investment in the shipyard capacity needed to build it faster. A survivable design that takes 3 years from keel laying to commissioning is solving half the problem. The other half is how quickly you can replace losses and grow the fleet. The Navy has recognized this. The DDG-X program, the next-generation destroyer intended to eventually replace the Burke, was formalized as a program of record in the early 2020s. Its design requirements explicitly include advanced materials consideration, which is the careful language program offices use when they're reconsidering aluminum's role in a world where fire-resistant alloys and composite panels have closed some of the gap with steel. But DDG-X is not a ship yet. It's a requirement document, a concept study, and a budget line. The hulls in the water today, and the hulls that will enter service over the next decade, are Arleigh Burke's. The steel is already welded. The layers of this decision converge on a single strategic reality that planners in the Pentagon and in Beijing are both running calculations around simultaneously. The Burke-class Aegis combat system, particularly in its Flight 3 configuration with the AN/SPY-6V1 radar, represents a genuine technological lead in integrated air and missile defense. The SPY-6 can detect targets with a radar cross-section roughly 35 times smaller than what SPY-1D could track. It can simultaneously track and engage ballistic missiles, cruise missiles, and low observable targets across a volume of airspace that was, a decade ago, operationally impossible for a single ship to cover. That capability sits inside a hull that weighs more than it needs to, costs more than it should, and takes longer to build than the threat timeline ideally allows. The Aegis system is among the most advanced combat systems at sea anywhere. The hull carrying it is a 1980s design that has been extended and upgraded to its practical limits. This isn't a failure. It's what happens when you invest heavily in one direction: electronics, software, sensors, without reinventing the platform that carries them. The SPY-6 radar is generationally newer than the hull it sits on. That gap isn't unique to the Burke class. It characterizes most of the American surface fleet. But it's sharpest there, because the Burke is the ship the fleet depends on most. The Type 055 that Chinese naval architects launched into serial production doesn't carry a combat system that matches Aegis in integration depth or proven performance. What it does carry is 112 VLS cells in a hull displacing 12,500 tons, with a superstructure designed from the outset for the sensor and weapon loads of the 2020s rather than retrofitted to carry them. Bluntly, it's a ship with more room to grow, because it started from a larger hull with more growth margin. What this means for the balance of forces in the Western Pacific isn't a simple comparison of hull counts or missile numbers. It's a question of which design philosophy proves more durable over the next 20 years of threat evolution. The Burke chose survivability and paid in flexibility. The Type 055 chose capacity and bet on deterring the hit rather than surviving it. Both bets are live. Neither has been tested at scale in the environment for which they were built. Put yourself in the position of a fleet planner working the Western Pacific problem in mid-2026. You have 69 Burke-class destroyers, each a $2 billion asset with a proven combat system and a hull running near its growth limits. You have a rival fleet adding Type 055S and Type 052D destroyers at a rate your shipyards can't currently match. And you have a threat environment where the cheapest effective weapon against your most expensive ships costs less than a new pickup truck. The steel that makes the Burke survivable also makes it heavy. The weight that makes it stable also consumes the margin that could carry more weapons. The weapons that make it lethal must be replenished from a logistics chain stretching across the widest ocean on Earth. Each layer of the problem connects to the next, and the connection point, the material decision made in a design office in the 1980s, turns out to be the thread that, when you pull it, runs through the whole strategic equation. One detail from the naval architecture literature stuck with me. The original DDG-51 design requirement specified a service life of 30 years. The first Burke, USS Arleigh Burke itself, is now over 30 years old and still in active service after a mid-life modernization that cost roughly half the price of building a new hull. The ship outlived its design life because replacing it was more expensive than extending it. The steel that was supposed to be a survivability feature became a longevity feature by accident. because a structure that resists fires also resists corrosion and structural fatigue better than aluminum at equivalent maintenance cost. That wasn't in the original calculation. It turned out to be one of the steel decision's best arguments, one nobody made at the time. The crews who operate these ships live inside the consequences of the material decision in ways that don't appear in engineering specifications. An Arleigh Burke at sea in the Western Pacific runs a demanding operational tempo. The deployment cycle, typically 7 months for a Pacific-based hull, places crews inside a ship whose damage control architecture is built around the steel survivability baseline. Every drill, every firefighting evolution, every compartment flooding exercise reflects the assumption that the hull will hold, that the overhead will not collapse, that the team working a fire in a lower compartment has structural integrity above them. That assumption isn't free. It's purchased with the weight penalty, the cost premium, the build time extension that makes each Burke slower to produce than the threat timeline would prefer. The crew doesn't feel the weight directly. They feel it as capability, the confidence that their ship was built to survive what it will be asked to survive. The phalanx CIWS mount, the last kinetic barrier between an incoming missile and the hull, fires at 4,500 rounds per minute and engages targets at ranges measured in hundreds of meters. It activates when everything else has failed. When the SM-6 missed, when the RAM interceptor missed, when the electronic warfare suite failed to seduce the seeker away. The phalanx is the argument for why you need the steel behind it, because the phalanx will not always stop everything, and what it doesn't stop will hit the ship. The training that Burke crews run for exactly that scenario, a hit, a fire, a structural challenge, is calibrated to a steel-hulled reality. Switch the material and the training changes. The margins change. The sequence of failures changes. The hull isn't interchangeable with a lighter alternative without rebuilding the operational doctrine that goes with it. Will the Navy eventually run out of runway on the DDG-51 hull and move to a fundamentally different platform? Comment yes or no, because this is the question that every shipbuilding budget cycle is implicitly answering, even when the program office isn't saying so directly. The resolution of the steel paradox isn't a single answer. It's a trade-off that has been renegotiated continuously since 1985, and the terms of that negotiation are shifting again. The DDG-X program, as it currently exists on paper, targets a displacement in the range of 13,000 to 15,000 tons, larger than the Burke, closer to the Type 055 size class. The larger hull creates growth margin. Growth margin is the resource the Burke ran out of. The choice of materials for DDG-X as superstructure is explicitly under evaluation, with fire-resistant aluminum alloys and composite panels that meet survivability specifications the 1960s materials never could have satisfied. The technology has genuinely moved. Modern aluminum-lithium alloys used in aerospace structures have fire resistance characteristics that close a portion of the gap with steel. Ceramic composite panels tested for naval applications can maintain structural integrity at temperatures that would have destroyed the Belknap superstructure in 1975. The material science that made aluminum dangerous in the era of the Leahy cruisers isn't the same material science available to a DDG-X design team in 2026. But the institutional memory is long. The engineers who will sign off on the DDG-X structural specification grew up professionally in a Navy that hasn't had an aluminum superstructure on a major combatant since the 1980s. The Belknap Fire is 50 years ago. Sheffield is 44 years ago. The argument for returning to lighter materials rests on engineering data that hasn't been validated in combat, on ships that haven't been hit, in fires that haven't happened, against threats that haven't connected. The argument for steel rests on exactly the same kind of data, until the moment it doesn't. Until the moment a ship survives something that would have destroyed a lighter hull, and the decision is vindicated by the worst possible metric. What this tells us about the broader competition in the Pacific. The material choice in a warship superstructure isn't just an engineering decision. It's a statement about what the Navy thinks the first exchange of a serious conflict will look like, and how many ships it expects to survive it. If the Navy believes Aegis will intercept every incoming threat, lighter materials are the right answer. They save weight, add speed, and create room for more missiles and sensors. If the Navy believes some threats will get through, that swarms of cheap drones and cruise missiles launched at scale will overwhelm any defensive system at the margins, then steel is the answer, because steel is what gives a hit ship the chance to keep fighting. The Burke program's 4-decade run suggests the Navy has consistently believed the second scenario. The investment in Aegis, in SPY-6, in SM-6, and the extended engagement capabilities of the AN/SPY-6V1 suggests it is simultaneously working to make the first scenario more achievable. Both beliefs are active policy. Both are being funded simultaneously. The tension between them is the tension inside the hull. The Arleigh Burke-class destroyer is, in the end, a ship built around a question. What happens when something gets through? The steel is the answer to that question, not the answer to how you prevent something from getting through. That answer is Aegis, SP-6, SM-6, the entire sensor-to-shooter chain that defines the ship's primary combat value. The steel is the answer to what comes after, to the fire in the lower compartment, to the damage control team working in a ship that has been hit and has not been sunk. That answer costs weight. It costs speed. It costs the growth margin that Flight 3 has now consumed. It costs build time in shipyards already under pressure to produce more hulls faster against a rival producing them at a rate not seen since the 1940s. And it raises a question with no clean answer. When a cheap incendiary threat meets an expensive hull, does the Navy keep buying survivability and heavy steel and accept slower, heavier ships? Or does it chase speed and capacity with lighter materials and bet everything on stopping the hit before it lands? Each path has its own bill. The steel path pays now in tonnage and cost and build time. The aluminum path defers the bill to the moment of impact and collects it, if it collects at all, in a way that can't be budgeted in advance. The shipyards are building Arleigh Burkes. The design offices are working on DDG-X. The choice between them is the choice between two theories of how the next war at sea will actually unfold. And neither theory will be proven until a ship is hit and either survives or doesn't. That's the read from the engineering record. We're curious what yours is. Drop it in the comments and stay with us for the next one.